Hi, in this video, we're going to take a beginning look at experimental design. All right, so what is experimental design? Experimental design is trying to set it up so that our data collection can give us as much information as possible. So, a couple of ways to think about this. First and foremost, try to get as little data, but get as much bang for our buck as possible. So that'll save us time, save us money, save us effort. Also to set up so that we have as much like power and reduce the amount of risk we have for our type 1, type 2 errors. Um, to like reduce the variance, have a clearer signal. There's a lot of reasons why experimental design is super important. Also reducing bias. All right. So experimental design, in my opinion, is the absolute most important step in all of data science. I don't care what field you're talking about. Why do I say that? Well, you know what? If you have junk data, if you have polluted data, you have problems with your data collection, if there's issues with your data, there's no point in analyzing it. Garbage in, garbage out. Okay. Well, if I have a poor game plan on my data collection, I'm probably going to have poor data. And so if I go out, I collect data, and there's errors, mistakes lacking in my collection of data, that's going to propagate through my entire project. And I might not be able to recover this. Now, experimental design, if I do this very, very well, if I grab the best variables to measure and record, and I have good solid methodology in my recording process, and I have good game plan going on, I can actually have less data and get more information compared to sloppy experimental design. And in general, overwhelmingly, it's better to have good data, but a little data, very like a small amount of good data is way better than a lot of data that's polluted and has problems, missing values, untrustworthy, things like that. All right, so it is absolutely critical for scientific research. Um, but honestly, holds true across all aspects of data science. I don't care if it's insurance. I don't care if it's a business problem. I don't care like if it's marketing or whatever it is you're doing. Experimental design is applicable to everything you do. Also, when you understand experimental design really, really well, you know what good data looks like. And if you know what good data looks like, that helps give you an idea, an insight into the data that you're working on, like how good is the clay that you have to make pottery with. um and so we're going to try and get good data, unbiased data, to give us answers that are correct and informative. um and so we're going to be planning our experiments to ensure that we have reliable and interpretable results. This includes like selecting the sample, determining how the treatments are assigned, and controlling for confounding factors. Why is it important? Well, properly designed experiments can reduce bias, increase precision, and provide valid and replicable results. They also help in optimizing resources such as time and cost. So here, I'm making sure that every single data point is worth recording, worth putting money into, worth putting time into. So some examples of experimental designs. So we can have completely randomized designs, randomized block designs, factorial designs, covariate adjusted designs. We'll talk about all of this in future lectures. All right, so my opinion, overwhelmingly, is that R is the better platform between R and Python. I believe that R is overwhelmingly the better platform for scientific research. SPSS definitely is going to give R a run for its money, because of its connection with the social sciences and psychology in particular. Um, I have a bias towards R. I like it more. Um, every platform for statistics is going to have a lot of good stuff in it, but I feel that R is actually the better platform for this because it's built, for statisticians by statisticians. But there's a problem. If you go out and you go job hunting, you're going to see that Python comes up way more than R. Why is that? Well, because the IT guys are more comfortable with Python than R. It's easier to get a statistician to use Python than it is to get, a computer scientist or an IT guy to use R. Just they just lock up on you. I don't know why. So we're going to use Python, even though it's like, a second string choice, it's still pretty good. The second string kicker on the football team can usually kick a ball pretty well. And so Python does a pretty good job. So we're going to use it for data analysis, visualization, statistical modeling, and it really is an excellent tool for this purpose. We have to kind of like build some things out to get things the way we want it, but pandas and SciPy stat models, they support us well on this. So some objectives for the course: we want to understand the core principles of experimental design and why it matters to research and data science. We want to design simple and complex experiments using Python, which I'll show in the video in a moment. We're going to implement randomization, blocking, and stratification in our experimental design. We're going to use different hypothesis tests and post hoc analysis to analyze the experimental data. We'll perform power analysis and estimate sample size for robust experiment planning. And we'll apply non-parametric tests when these tests up here cannot be trusted, because of like violations of assumptions. And so SciPy stat models, these are going to be super important. Penguin will also be a big one to use. All right, so we're going to be using these packages pretty consistently. Anytime you're doing anything in Python, you're using NumPy and Pandas. Remember that Python does not even have a mean or sum function in it by default. We have to pull in NumPy. Pandas we use for our data frames, our data structure, and data manipulation. SciPy, science with Python, stats models for statistical models. Whoops, that's not what I wanted to do. And Penguin is good for hypothesis testing. And so there's a wide range of tools. These are really good, and let's go ahead and take advantage of them. All right, so let's run through an example. I'm going to do 2 simulated experiments. All right, so I'm going to generate random data. So what we're going to do for the purpose of instruction, pretend that I had subjects, and each of the subjects I assigned a treatment, one of 2 different treatments. And then I measured the response variable after applying the treatment. All right, how the code works, that's not how it's going to happen. Everything's going to be generated at once. But in real life, we're going to get our subjects, let's say they're people. We're going to interview them, make sure they're good candidates for our experiments. Then we're going to measure features about them, record that. Then we're going to assign the treatment, apply the treatment, and then record the target variable, the response variable. So first and foremost, we're going to import the libraries we need. Now we're going to do our data collection. And so, we're always going to, try to come up with every possible relevant feature, that I can record. So it has to be, something relevant that I can actually get to. Maybe, features about a person that are too expensive or can't be measured are not going to be recorded, of course. And then, we're going to assign treatment groups to the subjects. We're going to apply the treatment. Then we're going to record the response variable and analyze the results. All right, so let's pretend that I have a collection of subjects. There's 100 subjects total, and I randomly assign either treatment A or treatment B to each of them. Okay, and then I'm going to go and so this represents the assignment of treatment A, treatment B. Here we're randomly assigning it. And then I go and I record the response variable. Now, here, I'm using random number generation just to kind of fill in the blocks, just so you can see what the process is like. But so pretend on this step, I'm going and I'm measuring the response variable for each individual subject after I apply the treatment. And then I'm going to go and analyze the data. Well, first and foremost, I'm going to look at the point estimates. I'm going to look at the stuff I've got. So, I've got the number of subjects for each treatment. I've got the mean, the standard deviation, and then I have the quantiles, the quartile values here, box plot summary. Now, one thing we always want to do, we always want to visualize our data. Our visualizations are not like concrete proof. The best proof is always going to be a hypothesis test, but we'll use visualizations as additional evidence to convince people that our conclusions are correct. Okay, so here is my box plot. Notice that the boxes are parallel to each other. This is an indication that there is no meaningful difference between the two groups in terms of the response variables. Now, we know, you and me, we know that the response variable was just random normal generation. And from the code, it has to work out this way. I mean, it doesn't have to, but it's more than likely going to give us like no distinction because these are exactly the same distributions for generation. But in actual real life experiments, I'm not going to know this until I'm in my analysis stage. So here I see two box plots and they're parallel to each other. I see that the boxes are lining up. If I see that the boxes are very different heights, that's an indication that we have different means. If the lines and the boxes are basically pointing to each other, that's evidence that we don't have a meaningful difference in the averages. Okay, so now, and also we can run a hypothesis test on this, and you'll notice that I get a pretty small t-test statistic for evaluating that there is a difference, and the p-value is 0.6. That's quite large. So we fail to reject the null hypothesis. We conclude that the two populations have the same average. Assuming that we have normally distributed, we're using the t-distribution for this. Okay, so now let's do this again, but now I'm going to have two different populations for A and B. So I've got treatment A, treatment B once again. Now I'm going to walk up and I'm going to collect my data. All right, well, let's say that under the hood, in reality, this is the distribution. Notice that the location is 60, so the central tendency is 60. That the central tendency of treatment A is 60, while the central tendency of treatment B is going to be 40. Okay, so in reality, so here I'm saying under the hood, these are two different populations. They're both normal. They have the same standard deviation, but they have two different central tendencies, two different means. And I don't know that until I collect my data and I analyze my data. I'm using random number generation so that you and me, we can see what's actually going on. In real life, we wouldn't know what's happening. That's the whole point of the experiment, whole point of the analysis. All right, so now I'm going to run through the difference. So I do a group by the treatment, and I do a describe. Once again, I get the count, I get the average, and whoa, I've got approximately 60 and under 40. Oh, that's a little bit of a difference. Okay, well, we can go a little bit deeper with this. Notice that the average of A is greater than the maximum of B. Huh. And that's kind of something kind of interesting. That might be a sign that we have something going on. Okay, so now let's go ahead and visualize it. Remember, we always want to visualize what's happening. I got my box plots. Now the boxes are in two very different horizontal positions, or vertical positions. Because of that, this is evidence that we have different central tendencies of these two populations. Now let's run a hypothesis test. And look at that. We have a t-test statistic greater than 11. It's approximately 12. And we can see darn close to machine accuracy of 0. So this is practically 0. If I notice the scientific notation of -21 in the exponent, that's a super small number. I reject the null hypothesis in favor of the alternative. I reject the hypothesis that the two populations have the same average, and I conclude that they have a different average. Now, this test doesn't tell me which direction, it just says there is a difference. Now it's on to me to figure that out, the rest of the details. All right, so we can look at the package is help documentation for further information. Now, here's your homework. All right, I want you to get paper helicopters. We are going to do a bunch of paper helicopters in this class. And with our paper helicopters, we are going to all do pretty consistent, not 100% consistent, but nearly consistent experiments for each individual student. What we're going to do at the end of the semester, we're going to take a meta-analysis of all of the experiments to see, can we glean something deeper on this? Okay, so let's take a look at the paper helicopter. Okay, so here is the template for the paper helicopter. We are going to cut wherever we have a solid line, and we're going to fold wherever we have like dash lines. Okay, okay, so sorry, we'll fold at the dashes. And what we're going to do is with our paper helicopter, we're gonna have different like parameter values for each of these. And so we're gonna have wing length. So we're gonna have 3 possible wing lengths. We have 6.5 centimeters along here. We have 8 centimeters along this dash line, and then 9.5 along the solid. We might have tape, yes or no, right here. We will have different body lengths that correspond to the dash line, this horizontal dash line, this horizontal dash line. So 6.5 centimeters for body length, 8 centimeters for body length, or 9.5 for body length. And then we can also fold along here. We will be doing a little bit of cutting, and we're going to have 3 different possible body widths going on. And then we can also put tape on the sides, yes or no, and we can put a paper clip on, yes or no. And so what we're going to do, we're all going to use the same template for paper helicopters, and we're all going to go with the same possible values for each of the parameters of our paper helicopters. We're going to do experiments. We're going to do this over and over, and we're going to take all of our data and collect it and put it into one big data set and analyze it at the end. Well, we're going to do something simpler right now. What we're going to do, each individual student is going to create 2 paper helicopters. Now, these 2 paper helicopters, you can make them as different as you want, or you can make them different in just one way. So what you're going to do, you're going to have 2 paper helicopters, and you're going to drop each of them at least 10 times. Then what we're going to do is when you're dropping, you're going to drop from the same height every single time, and you're going to use the same type of paper, like standard computer paper, for all of your paper helicopters, and you're going to use a stopwatch, get a friend to help you out, to measure how long it takes for the paper helicopters to hit the ground. And so you're going to collect data on this. So the first thing we're going to do is that we are going to decide on the parameters of my personal paper helicopter. So we have wing length, we have the 3 different values. We can have tape on the top, yes or no. That corresponds to the little square right there. Anytime you see a question mark in the template, that's a yes or no. Body length with 3 possible values. We can have tape on the side, and we're going to do both left, right, or none. And when I say left and right, that's looking at the template oriented, so that you can read it. Body width is either going to be 4, 5, or 6 centimeters, and paperclip is yes or no. Now, you're going to make 2 different helicopters, and you're going to drop each of them 10 or more times. So you're going to have at least 20 trials total. Okay, so when you drop these, drop them from the same height every single time. Make sure you record the height that you're dropping from, and record that in meters. And then record your data in a data frame. Now, here are the columns that you need to have it in. So your data frame needs to have exactly these columns. You don't have to do the same order because that won't be a problem. But please, please, please use exactly as it's written here, as I have it typed out. That way, every single student uses the same columns, same column names for their for their data frames. It'll be easier to combine everything and do that meta-analysis. If you don't follow instructions, you're going to have a harder time at the end of the semester. So think about that. Follow directions. If you're unsure, contact me. All right, and so here are the names of our columns. And so you'll notice I've got the trial number. So I'm going to drop a helicopter 20 or more times. So the first time I drop is 1. Second time I drop a helicopter is 2, 3, 4, 5, all the way up to 20 or higher. You're welcome to run this experiment multiple times. For now, for the homework assignment, I want 2 distinct helicopters, just so that we can run the t-test, by the way. But yeah, so we have all of these here. And so here are parameters of the helicopter. Here is the trial number that we're going with. Here's the height that you're dropping from. Please record the height. The time from a stopwatch. And then your name as experimenter. Okay, so there might be the situation where different students just end up getting different results because they're doing something different. Maybe that I'm going and I'm dropping everything outside because I live in an apartment, don't have enough room, something like that. And, because I go outside into a breezeway, that breezeway has a little bit of breeze, but not a lot of breeze, and that could affect the results. Somebody else, maybe they don't have a breezeway, they live in an apartment, they go outside, they get up on a ladder, and they drop repeatedly. Oh, be safe while you do this. Don't do anything dangerous while you do the homework. Be safe. Somebody could drop it in a windy area, and so that could be part of it. Also, somebody else, they might do it from inside. Heck, you know what you could do? You could go to the student union and do this. That would be fun. Like, why not? Go to the student union and drop paper helicopters. And so, this is a way for you to run the experiment. Now, if you want to, you could also, it might be faster for you to make multiple versions of the same helicopter. You're welcome to do that. And so here, let's run through an example. So in my example, I'm going to change the wing length, and everything else is going to be the same. So for my experiments, I'm going to have the minimum and maximum wing length of my 2 helicopters. Everything else is going to be the same. So I'm lazy. I'm not going to mess with tape. I'm going to put the body length to like the standard value. I'm not going to put side tape on. Body width is going to be 5 centimeters. I'm not going to mess with a paper clip. And my height is going to be 3 meters for dropping. Measure in meters. And so now you'll notice that my trial number is not filled out yet. And you'll notice that my time in seconds is not there yet, because that's my response variable. And I'm going to have my name on here in case there's something about me, something about what I'm doing that influences results. I'm going to use the product function within itertools to generate all the different experiments I'm going to do. All right, and then I'm going to name my columns. All right, so here, this is what the distinct levels of the experiment look like. So you'll notice that tape is always the same because I'm not messing with that. I'm using the same value every single time. Body length is always the same. Side tape is always the same. Body width is always the same. Paper clip, yes, no, is always the same. Height is always the same. Experimenter is always the same. Now the trial number, that's going to happen when I actually do my experiment, and the time in seconds is going to happen with the stopwatch. I'm going to need a friend to help me on this. One person's going to drop, one person's going to time it. Okay, so now when I've got this, you'll notice I've got all this distinct setups of my experiment are already set up for me. Now, what we're going to do is I'm going to do this at least 10 times each. And so I'm going to do a repetition. So numpy's repeat in the index. So here are the distinct levels. I need to have each of these rows 10 times Okay, this gives me 10 times, but these are going to be all the, the first row, then the second row, in that manner. So it's going to be first row 10 times, second row 10 times if I leave it as is. Well, if I use the sample function, it's going to, with frac equals 1, it'll permute those rows, and I've got that set up. And so now I'm going to reset the index. I'm going to use the index after it's shuffled to determine the order that I'm going to execute. And so I can see that in this randomization, the first 3 trials are with the shorter wing length. Then I've got the longer, shorter, longer, shorter, shorter, longer, 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 and then so on. I'm going to keep on doing this over and over and over. Now, as I work through this, I'm going to write down what was the time after each trial, and then I'll have my results. After I get my results, I'm going to visualize the 2 different box plots as evidence of a difference or lack thereof, and then I'm going to do a t-test just to see how things work out. All right, so experimental design, the whole point of it is to get better data analysis, better data science, better experiments with less work, get less bias, more precision, more accuracy, less money, less cost, less effort, less time. And all we have to do is just have a good, solid game plan. This first assignment, the big step for it is just to come up with the game plan of your experiment, run your experiment, then see what the differences are. That's all I've got for you. Life is short. Do math.